Ladies and gentlemen, good morning, good afternoon, good evening, depending on where in the world you are. I would like to welcome you to our latest webinar in the series Scientists Empowering Scientists, General Maintenance on your SATA pipette pullers and Combining Imaging with Patch Clamp. I hope this finds you and your loved ones in best health in these times. Probably many of you are sheltered at home. We at Sutter work from home these days, but can be reached by phone and email, and core crew is in the office, but we keep the number of people in the office at a minimum. My name is Jan Dolzer. I'm the product manager for Patch Clamp Systems here at Sutter Instrument. I'm going to give a very brief introduction today, talking about a number of housekeeping items, and then I'll briefly talk about the product portfolio at Sutter Instrument and a little more about the amplifiers. But this will really only be a couple minutes. Then Adair Österle will talk about the general maintenance on your Sutter pipette puller. Then Telly Gaatzatos will talk about combining imaging with patch clamp experimentation. And then we will have a combined Q&A session and discussion. And at the end of the webinar, you're going to be directed to a very brief survey. The audio is transmitted over your internet connection, so many of you will probably use computer audio. That means you may need to turn up the volume on your computer. If your computer does not have speakers, or if you don't hear us now, then dial in the United States, either at this phone number, or there's phone numbers for another, I think, 33 countries accessible through the webinar control panel on, by default, the right side of your screen. And the access code is the same, irrespectively of where you dial in from. I'll leave this up for another 10 seconds for those of you who may not have audio right now, and then move on. The questions, I mentioned the Q&A session at the end of the webinar. Please ask your questions in the question section on the webinar control panel. Please do not use the chat. That confuses things and makes it very hard to coordinate. Please mention, unless it's very clear from your question, which speaker your question is directed to. Sometimes it's a little hard to guess. All questions will be addressed during the Q&A session at the end of the webinar, or offline by email. And there's also a number of questions that were asked when you registered that we may not have had a chance to get to. We will also get back to you about that by email. We have documentation materials. They're also accessible in the GoToWebinar control panel. Unfortunately, the PDF for Adair's talk did not upload because it was too big. She has a lot of videos embedded in her presentation, which show as images in the PDF, and that made the file too large. So unfortunately, we do not have a handout for Adair's talk today. I have to point you to the webinar recording. The recording will be available on our YouTube channel, and for our customers in China, also on our Yuko channel. And we expect that to be available within the next 2 weeks. And everybody who registered for the webinar, even if you couldn't make it today, will receive an email notification when this is available. At the end of the webinar, you will be directed to a very brief survey. In essence, just do you want us to get in touch with you, and you're okay to add to your mailing list. Most of you will probably be in our mailing list already. This is how you received the invitation. So let me switch gears and briefly talk about the Sutter Instrument product portfolio with a slight focus on amplifier systems. We have a number of product lines for micropipette fabrication. That's probably why most of you are here. We make micromanipulators, imaging products, microscopes, instrumentation for noise isolation, perfusion systems, and microinjection equipment. And a couple of years ago, we added patch clamp systems. That means what we can offer you is a complete turnkey system for a patch clamp rig combined with imaging or multiphoton imaging, things like that. Our patch clamp systems product line consists today of the IPA family, the IPA and the double IPA, which are amplifier systems optimized for wholesale recordings. And we have our flagship, the D-Patch ultra-fast low noise amplifier system. That means it has low enough noise for single channel recordings and ultra-fast means it has an analog bandwidth between 500 kilohertz and a megahertz, and a sampling rate of 5 megahertz. And I just briefly want to highlight the dynamic clamp capability that we added to the D-Patch. Released that a couple months ago, and we had a webinar a little over a month ago, which is also available on our YouTube channel. Then we have the Dendrite Data Acquisition, Management, and Analysis System as our most recent product. We made that because a lot of people liked the SATA-Patch software that comes with our amplifier systems, but they have an amplifier that still works, but their data acquisition system might no longer work because you can't find a supported computer anymore. So the Dendrite will work as a computer interface bundled with SATA-Patch software. And SATA-Patch software increasingly popular in the patch clamp community. We have a lot of repeat customers, which shows us we must have done something right. Let me highlight one aspect of the amplifier systems. They come as bundles. The IPA is an amplifier with the interface, the computer interface integrated, and it comes bundled with SATA-Patch software. So what may be 3 components in your existing rig, an amplifier, a digitizer, and a software, is one bundle at a very attractive price. The same goes for the double IPA. The Dendrite does not have the amplifier section, only the interface. And the D-Patch, of course, is also amplifier and interface, and it's all one bundled system. So if you compare prices, keep that in mind. It's not 3 components that you pay for. There's a number of publications now out with the IPA system, which we started shipping in 2015. And I don't want you to read all this because it's much too small. There's a list which is probably outdated. Every time I look, there's new publications right now. There's a list on our website, and we expect the first publications with the D-Patch to come out sometime soon. Let me introduce today's speakers. The second speaker will be Telly Gaatzatos. He graduated from Queens College in New York in computer science in 1987, joined Instrutech Corporation right after that, and filled several roles there, eventually the general manager. In 2007, when Instrutech was taken over by Heka Electronic, he became the general manager at Heka Instruments, and that's where Telly and I first met. And since 2015, he plays a very important role in product development and also technical support for the amplifier systems here at SATA Instrument. And the first speaker is going to be Adair Österle. She caught the biology bug probably earlier than '84 when she did a microbiology course in Woods Hole, graduated in '85 from Scripps College with a major in biology, went to UCSB for postgraduate studies, then San Francisco State, and several positions at UCSF and the San Francisco VA Medical Center. In 1998, eons ago, she joined SATA Instrument and is today the applications engineer and the product manager for the pipette pullers. And in that position, there were 2 consultant and contractor jobs that she did in Zika eradication research at the International Atomic Energy Agency and also with Verily and Google. And with that, let me switch over to Adair.
Thank you, Jan, for the presentation and the overview. Today, I'm going to talk about general maintenance on your pipette pullers, mainly your P97s, P1000s, and the P2000. We still have older pullers that are still running, still working, P77s, PDPCs, but most of this maintenance concerns will address the more recent revs of the pipette pullers. So again, my name is Adair Österle, and I've been with Sutter for about a little over 20 years. And I think a number of you out there know me and have communicated with me via email. But if you have any specific questions around programming on the P2000 puller or the P1000 puller or P97, send me an email or call me. This webinar mainly is going over just maintenance concerns. And so that's where we're going to go today. The first thing I want to go over here is an outline of what I'm going to be speaking about. First, we're going to touch upon variability, just a few issues there. That's one of the main reasons you probably are going to want to take a look at some of the maintenance and cleaning issues on the puller, because you might want to get rid of that variability that you're running into. 99% of the time, there's a mechanical issue, there's some friction, or there's a alignment issue with the filament over the air jet around the glass, or there's an alignment issue with the laser on the P2000 to the glass or the mirror. But a lot of the time it's just a sort of a bad program. So we'll go over some of those details. So we're going to discuss cleaning different parts of the puller, how to check the pulleys, the cable tension, V-groove bearings, and look at the play of the puller bars and how they're supposed to feel. We're going to discuss whether anything should be oiled or greased. On the P2000, we're going to go over cleaning of the retromirror, which is what is focusing the laser heat that's coming from the back inside the chassis towards the glass. Whatever's missing the glass is hitting the mirror, refocusing back onto the glass and heating it from both sides. If your mirror is dirty, you're going to have a problem with heating and melting your glass efficiently or with stability. There's a thermal paper test that we'll discuss, the micrometer adjustment to get the laser pointed properly at your glass. And we're also going to touch upon bending quartz glass, which is kind of an exciting thing. A lot of people don't know that you can do that, and it's sort of a hidden trick. So it won't be so hidden after I discuss it with you all. Here's the P1000 puller. This will pull borosilicate and aluminum silicate glass. It will not pull quartz glass. You'll need the P2000 for that right here. Variability, again, you're going to want to take a look at your parameter settings. In a previous webinar, How to Make Better Pipettes, you can find a lot of information there on how to program the puller, how to find stable programs, how to find midpoint velocity to make your patch program stable. But a lot of times you just have one parameter that's too high or too low, or the program's just completely wrong. So in those situations, you can find a good program in the cookbook, or you can call me or email me and I'll give you a place to get started. There's a Pipette Cookbook, which is a reference you can use, our webinars, and you can also contact us. Again, a lot of the time there's issues around the alignment of the filament over the air jet and around the glass on the filament-based pullers. And we have YouTube videos. We'll have this webinar on our YouTube channel. There's a few things we want to go over, little housekeeping issues, where you want to make sure there's no dust or fragments of the glass blocking or obstructing the movement of the various parts of the pullers. And there's sometimes oils get built up and they polymerize, they harden, and they cause some problems with the bearings and the pulleys. So those are things that we will discuss today. Some parts can get worn out, and then sometimes the eccentrics will get adjusted by a well-intentioned user, and they'll most often get adjusted incorrectly. That's another thing we're going to go over. With some of the adjustments on the puller, you're going to need to get a hold of us first, and then I will walk you through how to make the adjustments properly. I'm not giving you those adjustments here in the webinar because that's just a little scary. So I'd rather walk everyone through it independently in that case. So we're going to focus on the pulleys, cable tension, and then the puller bar play. Now the cable tension, there's not really a tension in the cable. There's more of a kind of a slack or a little bit of a play in the cable, which I'll discuss with you, but it's a little bit of a misnomer when we talk about the tension of the cable. And then with the laser, most of the time when you have some variability there, it's other than programming issues, there can be a dirty mirror, and also maybe the laser's not properly focused onto the glass. So again, we've got the Pipette Cookbook, which many of you know about, and it was presented in a previous webinar, making sure your filament's centered over your air jet, and then making sure that both pipettes that you're pulling, when you pull a long tapered pipette, they're the same length. Once you've done this step on page 17 and 18 in the cookbook, you can move forward and make your patch pipettes or your injection pipettes your microelectrodes for recording. On the P2000, there's some specific features. There's this door that you have to shut. There's some safety switches that get depressed when the door's shut, and this is to protect everybody from the CO2 laser that is inside. There's a lot of things blocking the laser from escaping. That lid is just sort of a third layer of safety. So we had to put those safety switches there. If you try to press pull, which I always do, without closing the lid, you'll get this error message right here. I'm so used to using the P97s and the P1000s that I often forget to shut the lid. And then people are used to the P2000 and they go use a P1000 or P97. They're always shutting the lid and they don't have to. So the lid is basically a dust cover on both of them, but on the P2000 it also serves as an additional level of safety. There's a little bit of a difference in the design of the puller bars between the filament-based pullers and the P2000. Older P2000s do have this puller bar where the groove is angled and faced upward a bit. It's a little bit of a deeper groove. On the newer rev of the pullers, the P2000 pullers, there's a more of a shallow groove. The bottom sort of shelf of that groove is trimmed back and the groove is facing perfectly outward horizontally. And so what happens when you go from 1 millimeter glass to 1.2 to 1.5 on the older style puller bars over here, the glass will rise up. On the laser puller, it will block more of the power that is hitting the other side of the glass. The other thing about the P2000 puller bars is this groove is, because this lower part of it, and it's a little bit more shallow, and the lower part of the shelf is kind of trimmed back, it's harder to load the glass. So what I do is I make sure that I don't have the knob on the clamp loosened so much, so it stays in the groove more easily. This is in a tribute to Madonna, right? Get into the groove. So just make sure that glass is loaded properly. At the bottom, you see the glass is dropped down, and it's in that lower sort of machined cutout that we have in the puller bar. It's intended to be in that top groove, so that's the way it needs to be loaded. Another thing here is both the filament-based pullers and laser pullers. When you're pulling a patch pipette, it's very important to find that midpoint velocity. I've reinforced that message a lot with the filament-based pullers. The laser pullers, I'm not sure if that message has gotten across as clearly. The next webinar we do, I'll go over that, and I am aiming to make a pipette cookbook for the P2000. But finding the midpoint velocity when you're using a one-line program that loops on your pullers will make sure that that program is stable. So there are cleaning issues on the puller bars. There's the V-groove bearings, which can get dirty, the beveled edge of the puller bars, and also the knobs, posts, and clamps often need to be addressed. So here I'm going to show you just basically you're going to get 70% ethanol, and you're going to clean the beveled edge of the puller bars. And you want to clean the back and the front. Everyone sees the dirt on the front, and they never see the dirt on the back. And sometimes there's a lot of buildup on the back, at the bottom and at the top. On the back of that beveled edge, there's a lot of grime that people might not notice. You can just get an eyelash on that beveled edge of the puller bar, and it'll cause a bit of a bump. And you can see I'm picking up a little bit of dirt there. And then you also want to clean the V-groove bearings. And I'm taking ethanol on a Q-tip. I've pulled the cotton of the Q-tip to a little bit of a point. And you can see I got quite a bit of dirt out of this one. And then you want to make sure that you address also the bottom V-groove bearings. And you want to do this, obviously, on the right and left puller bars. The next thing is we're going to take off the knob, the washer, and the clamp, and we're going to inspect the rubber pad that's on the back of this clamp. There's a knob. You've got a little washer there. Sometimes people put that under the clamp, which is incorrect, so make sure you don't do that. And when you turn this, well, I guess I'll be showing that to you here. Here we go. There's a little bit of a groove there, you see. And that's caused by clamping onto the glass, and you wear away at the center of that rubber pad. And you also want to take out the springs. Sometimes when you take the clamp off, the springs fall out, so just be careful. I was at the NIH one time in the evening fixing a puller, and I think I spent about a half hour looking for those springs that fell on the ground. I didn't have any spares. That wasn't a good evening for me. And here I'm taking just a broken off sharp edge of applicator, and wiping and scraping off the debris that's in the groove that holds onto the glass. Don't use a file, don't use metal. You're going to put a scratch there, you'll put a burr in the metal, and then what will happen is you'll cut the glass that way, and then it'll break every time you load it. Here first, we're going to clean the threaded post. You can get a lot of buildup of debris. What happens is the knob sometimes wears away at that threaded post, and you'll get a buildup of black debris. It looks like pencil lead dust underneath the puller bars, and it's good to clean those out. And then you'll use lithium grease, and you will be placing the lithium grease onto the threaded post. But first, you do want to dry out the inside of the knob and the threaded post. And then you're going to put grease on the threaded post. It's a white lithium grease. And then you're going to put some onto the helicoil in the knob. And then you'll put all the parts back on. And sometimes that threaded post gets so built up with fragments of metal that it feels very rough. And so if you do this, this will help prevent the wearing of that threaded post over time. It is possible that your threaded posts have been worn down completely, and when that happens, the thread is completely gone, and you'll need to contact us to get the threaded post replaced. But you can buy the knobs and the clamps and the springs and the washers. The threaded post is much more detailed in getting replaced. So here are some images of the threaded post. You don't see the post here, but you see all the debris down below. It looks like someone sharpened a bunch of pencils and then dumped out the lead. But you'll see that right there on the base. You'll see it on both sides where the filament is loaded. And here is an image of where the thread is completely gone. And it's gone here too. And on this situation, the thread is gone. They took the washer off so they could expose a little bit more thread, and then they kept on using it, and then eventually they wore away at the actual clamp. So in these situations, you're going to want to buy some new knobs and clamps. And there's some part numbers here, and we sell them in pairs. There's imperial and metric versions, so you're going to have to give us the serial number of your puller so we know which type of knobs and clamps to send to you. And you can see up here, you can see this line here of where the glass is worn away on the rubber pad. Sometimes it's completely split, sometimes the pad is missing. And the new pads, we actually taper the rubber so the glass doesn't run into the side of that rubber padding. You're also going to check your V-groove bearings, and you're going to see how those are adjusted. These don't get out of adjustment unless someone's come in and tried to do some work on it without knowing what they're doing. So let me just show you how the puller bars are actually supposed to feel and look when the bearings, those V-groove bearings that the pullers are riding in, are properly adjusted. So you're going to pull the puller bars inward and wiggle like a little sort of San Francisco earthquake or aftershock, and they'll wiggle a little bit and they'll have just a little bit of play. That's good. Here is the same thing on the laser puller. There's a number of generations of laser pullers where we've had them a little tighter and then some of them are a little looser, just depending on how they've been built in relation to the laser and the other aspects of the puller. But I'll also show you where the puller bars are actually too tight, right there. That's fine, and the right one's too tight, the left one's good. And down here, the left one's good and the right one is too loose. All right, and in that situation, you got to get a hold of Sutter, and we'll help you out. You can also tell whether or not these V-groove bearings here, this is the eccentric one, and that's usually the one that eventually needs to get adjusted. But another way to tell is by holding the right puller bar, lifting up the weight that's down below, and it's freeing up that left puller bar so you can just toss it back and forth and see how it slides. It should just float back and forth. In this situation, you'll see I'm going to release the weight on the other side, and then I'm pushing this puller bar. It's not freely floating. There's a lot of friction. friction is your enemy, it's going to cause a lot of problems with variability. It's going to introduce a lot of variability, and you don't want that. And so another way to check your V-groove bearings to see if they're properly adjusted, when you load the glass, it kind of takes the weight off of the puller bars, and so you can actually spin the bearings on both sides when glass is loaded. So this is a nice little trick I use. You see that? That's not turning at all, just turning a little bit, but the right, again, is too tight, and the left was fine. I'm going to give you a little warning here about not adjusting the eccentrics. And rather than just saying it, I'm giving you a little animation. I know you're just going to be blown away by my skills in animation. Pixar, Walt Disney, Lucas, Warner, they're all after me. You know, they all want me to come work for them. Yeah, you'll see why. But anyhow, I want to reinforce, do not adjust anything. Call Sutter first. Yep, there we go. There's our martial art Goofy coming in to prevent you from doing anything you shouldn't be doing. So don't adjust anything, call Sutter first, and we'll help you out. You can also email us, and that information is in the webinar too. The next thing to check are the pulleys. Sometimes the oil in the center of the bearing becomes hardened and polymerized. The top one I'm going to show you here, it barely turns. I've even labeled it so you can tell that it's bad. And then this one is an example of the newer style pulleys that spins like a skateboard wheel. The P2000 pullers do have black pulleys still, and don't think that the silver pulleys are good and the black pulleys are bad. You need to spin all of them to test them. But the silver pulleys are the newer style, so I can tell in the P97s and the P1000s whether or not they've been changed. You also need to check the pulleys inside the P1000 and the P97 or your P87 puller. The P2000 also has lower pulleys, but you're not going to check those because you don't want to open it up. There's too many safety concerns. The laser puller has a hard pull most of the time when you're pulling quartz glass, and it overcomes any subtle friction that you might be running into. So the laser puller is a little less vulnerable to the pulleys being sticky. But here I've dropped down the front panel. You drop it down like a toaster oven. And now I'm going to show you what the pulleys look like inside. I'm going to push the puller bars outward to release the cable tension on the pulley, and then I'm going to spin it. You can see this spins hardly at all. They can also feel very rough and bumpy, so that's another thing. Here's the pulley on the P2000. If you watch the inside of the wheel, you can see it turning a little bit better than focusing on the black part of the wheel. You look at the bearing part, and this is good, and then this is also a good spinning wheel. So if you have any friction in your pulleys, get a hold of us and we'll help you out. You can buy the pulleys, you can replace those for the P97s and the P1000s and the P87s. The P2000s, you're going to need to contact Sutter. And here's another very sophisticated animation of what not to do, which is you don't want to oil anything here. So here's our martial art Goofy making sure that you don't oil anything. So on the filament-based pullers, here are the parts that you would order. It takes about 1.5 to 2 hours for me to walk you through Skype, FaceTime, WhatsApp, Zoom on how to replace these. I also have 8 pages of instructions. We also have reps and dealers who can do this. Not a lot of them, but some of them can. So it's worth giving that a try too. And the part numbers are there. Again, there are metric and imperial pullers, so keep that in mind with buying the parts. Make sure you get the right thing. The cable tension, there's 2 tests. One's poking and one's bouncing. So I'll show you that. This here is a demonstration of how to check the cable tension to see if the pulleys are actually in the proper position. And you have just about 1 to 2 millimeters of play there, or deflection on the cable. So 1 to 2 millimeters deflection is good. Anything larger than that is bad. I'm going to show you here the right-hand side. They should be equal. And there's sort of a tapping noise in there, which you'll hear. It's sort of a tapping, a clunking noise. If you get something that's kind of boingy, that's not so good. It means that the cable's too loose. Here, I'm showing you the position of this eccentric, and here I'm able to depress the cable too far, and that means that it's too loose. It'll also sound different. Another way to test the cable tension is by doing something where you look for the bounce of the cable, where you take the left puller bar or the right puller bar and you hold it inward. So you hold the left one inward in this case, you look at the left cable, bottom cable, and you push or slam the right puller bar inward, and that left cable will bounce. I'm going to play that again for you so you can see it. And you want to look for an equal amount of level of bouncing on the left cable and on the right cable. So we're testing the left one here, and that's good. And we're going to test the right one on this one. Hold the right puller bar in, look at the right bottom cable, and then slam the left puller bar inward and look for that bounce. And that's good. In this situation, the left cable's good, the right is too loose. It looks like the left is too tight, but one's bouncing a lot and one isn't bouncing at all. So if there's a huge difference between the right and left, that means that something needs to be adjusted. In this situation, at the top, the right one is too loose, and the screw here, the eccentric, is angled from a 2 to 8 o'clock position. And on this one, the cable's too tight and the eccentric has been adjusted, so it's turned outward and it's from a 10 to 4 o'clock position. It's no longer horizontal, which it is up here, which it should be. And the other thing to look for here, I'm going to advance this a little bit farther forward. At the end of this video, it shows right here that you see that right there on the right-hand side, the puller bar is not even hitting the stop. There's a screw there. Again, we have another fun animation about what not to do. Don't adjust these until you give me a call or get a hold of someone at Sutter, and we'll help you through it. Don't adjust anything until you get a hold of us. We really appreciate that. It's a hard thing to do, and it takes a bit of time. So it's best if we walk you through it. The laser puller, there's a few concerns we're going to go over here. One, removing the shipping screw or loosening it, making sure it's loose, cleaning the retromirror, and then we're going to look at the vertical alignment of the laser using the thermal paper test, and I'm going to show you a trick on bending the quartz glass. So here's the micrometer on the back of the puller, and there's a shipping screw there, and you're going to need to loosen that shipping screw. It's very long, and you need to unscrew it all the way. And if it's putting any pressure on the plate inside that it's holding in place during shipping, the laser alignment to the glass will be off. Here's information on cleaning your retromirror. Depending on how often you are using your laser puller, you're going to want to clean your mirror on a fairly regular basis if you have heavy use. Every few weeks, once a month at the minimum. A lot of people don't know about this, but here's what you need to do. You're going to remove the shroud, and you're going to lift it off. Don't lose the screws like I just did, but make sure you put that somewhere where you don't lose the screws. And then you're going to get some 70% ethanol, or a little higher, but somewhere between 70-80% ethanol is good. You're going to get lens paper or chem wipe, and you're going to clean the mirror. And then you'll put another mirror there that now ships with a P2000 to inspect it. This needs to be cleaned because this is actually reflecting the heat of the laser onto the front of the glass. The laser's coming from the back, and then it's hitting the back of the glass. Whatever's missing that glass is hitting that mirror, focusing back onto the other side of the glass. So oils will build up on that retromirror from your fingers, from handling the glass. The oils then burn into the retromirror if it's not cleaned. Then you need to buy a new mirror and get that installed or send it back to Sutter for repair. Once that mirror is damaged, it no longer has a good reflective surface, and you're going to have variability or inefficient heating on the other side of the glass. So the lesson here is clean that mirror on a regular basis, and that also depends on the level of use. Here's the direction of the way the laser is coming, and that's the direction of the reflected light. The thermal paper test, you're going to remove that shroud, And this is going to tell you whether or not your laser is aligned to hit the glass properly. And to adjust the alignment of this, you would use that micrometer on the back of the puller, which I'll show you. But you're removing the shroud. You're going to insert a thermal paper between the glass and the retromirror, and then you're going to select program 51, which is shown down at the bottom too. 200 heat, filament 5, velocity 0, delay of 40, and a pull of 0. And this just throws a little bit of heat towards the glass to see how it is focused. And I'll show you inserting the paper. You're going to have to get it behind the glass and in front of the mirror, just like that. Okay? And now we're going to run the thermal paper test. And you've installed your program, you've put in the thermal paper. Now, I've put it in incorrectly just to show you what happens. I've put the dull side outward, and in this situation, you're not going to see it burn and you think it's not working. So here's what it looks like. I just did the thermal test, going to do it again, and you can barely see some decoloration right in here. You can barely see it. There's just like a little bit of browning. It's the paper's turned the wrong direction. So in this situation, I've got the paper, the shiny side outward, and then I'm going to do the thermal paper test. And here you will see that you get 2 equal burn marks on the top and the bottom of the glass. That's exactly what you want. We call those hamburger buns. And you want the hamburger buns to be even. Now what's happening is the light from the laser is hitting this mirror, and it is scanning, and it's hitting the glass. Whatever's missing the glass is hitting the retro mirror and focusing back onto the other side of the glass. So when you adjust this micrometer, when you turn the dial clockwise, it pushes down on the lever, and the mirror will tilt. So it pushes down on the lever, the mirror will tilt upwards, and this will point the mirror higher, so the laser heat will point higher. This is if your hamburger bun on the bottom is big and on the top above the glass it's too small. I'll show you that in another slide. If your hamburger bun is bigger on top, there's more heat hitting the top above the glass than below, you're going to need to turn the dial counterclockwise, which will then push that lever up. And the mirror will tilt down. It's like a teeter-totter, like a seesaw. And that will aim the glass down lower. Here are some examples from a customer who just sent me these. This is an amazing thing. I love it when I get these. And you're looking for the burn mark to be equal. And in this situation, you see the burn mark is larger here on the bottom. It's larger here on the bottom. And here it's larger on the bottom. So what they had to do was make an adjustment on the micrometer and then do another thermal paper test. They just did tiny adjustments until finally the burn marks were equal. And in that situation, you're just making maybe like a 1/8 or 1/16 or a quarter turn on that micrometer dial. So you're turning the dial. In this situation, you want to turn the dial clockwise to push that lever down, to point the mirror up, to have the laser hitting higher, and so you'll get equal hamburger buns. So here I'm turning it to the right, clockwise, and you're going to aim the laser higher, and then you're going to create a more even vertical distribution of heat. And your goal is to get 2 equal hamburger buns, is what we call them, and you can see why. This is what you're aiming for right here, and what you're aiming for right here, and right here. He did the test on various sizes of glass. You just have to do it on the size of glass that you're using. The next thing I'm going to show you, this is the last thing, is bending the glass, and this is super exciting. So you're going to bend the glass along the taper, and you're going to install this fire polishing spacer, which is right here, and that's going to hold the glass forward after you've pulled the long taper, so then you can re-expose the taper to this laser heat and bend the glass. So you're going to install this program here, which has a small filament, which is 0 or 1. You're going to have a 0 velocity, you're going to have a delay, which is keeping the heat on for a certain duration of time. And you're going to put that fire polishing spacer in, and you're going to have that set screw adjusted so it's positioning the glass forward enough that it's seeing the heat. Here I am just putting the spacer in. And here's the end result right here, which is super exciting. I love this. I love doing this. In fact, if I'm just, having a little bit of a down day, I'm going to come to my P2000 Polar and I'm going to bend some quartz glass because it's just so much fun. I love doing this. A lot of people need a angled pipette to have better access in their prep or under the condenser, or they need to come in level and parallel to their sample for injection or stimulation, and this is a good way to bend the pipette. Now, there's different degrees of bending. The parameter settings to use vary. The heat between 400 and 700, the filament, a low, small filament, which is scanning a shorter width of the glass. And then the delay is the duration the heat's focusing on the glass. So if you use too much heat, this is what happens. It just melts, the lumen closes. And then if you use a little less and a little less heat, it won't close up as much and you can still bend the glass. How much can you bend the glass depends on your heat, your filament, and your delay settings. It usually likes to bend around 10 to 15 degrees on average. If you try to aim for 30 degrees, usually that lumen closes up. And there's the best program that I like to use right there. If you use a higher heat, you're going to get more bending and more collapsing. You use a larger filament, you're going to have a more gradual bend. And you use a higher delay, this is going to leave the heat on longer. There's going to be a little bit more of a bend, but then be careful, you can collapse that lumen. So you want to keep it open. That's it. Okay, sorry I went over a little bit, but I had a lot to cover.
Thank you very much. That was a very nice talk, and I agree with you. The last slides were worth viewing. We just need to press on a little bit so we don't run over too much.
Hello, everyone. Thank you for attending our webinar today. It's always difficult to follow Adair. She has tons and tons of information on our puller. So I'm going to go brief on some of my slides. So our agenda for today will be to have an overview of Sutter Optical and Imaging products. There is where I'm going to just mention the categories and not go into any details to save us some time. Then we're going to go into the Lambda 421 beam combining system. I'm going to describe some of the front and rear panel controls. And then we're going to go into how to interface using the parallel, the TTL port, and then finally with the USB port. Sutter makes a number of different imaging or optical products. So like I said, I'll just mention them by names. We have filter wheels and shutters. We have a variety of light sources. We have high-speed wavelength switchers like the Lambda DG4 and DG5 Plus. And then we have a number of LED-based products here. I'll just talk about the Lambda FLED, which is a high-powered LED driver for fluorescence microscopy. It is based around the TLED Plus design, configured with one of several wavelength-specific LEDs. LEDs range from 365 to 940 nanometers. And then we'll go into our newest product, which is our beam combiners. This is the Lambda OBC, which stands for Optical Beam Combiner. This is a new patent concept for combining separate light sources with different spectra into a single common output beam. Each light source is collimated before entering the optical path through a bandpass filter. The filters for each light source also function as mirrors that reflect the collimated beams from the previous light sources. The Lambda OBC uses Semrock STR filters that are easily exchangeable. Associated light sources can be arranged in any order around the pentagon for flexible configurability. As you could see here in the slide, it's changing to all the different light sources that go into the pentagon. There are a number of spectral options available, anywhere from 340 to 940 nanometers, and these LED modules are constantly being upgraded. There's always changes from LED manufacturers. So here is a brief illustration of how the beam combining works. Depending on which LED module is active, there are either 0 or up to 3 reflections that happen inside the pentagon. Now, a complete description of this is available on our website. And now we're going to talk into our beam combining systems, because my talk will be about interfacing the Lambda 421 with software. So here we have the Lambda 421, the Lambda 821. As I mentioned earlier, these are based on the Lambda OBC and T LED Plus technologies in a single convenient cabinet. These systems are designed for extremely rapid wavelengths. Switching time is less than 25 microseconds. And the light output is derived from up to 4, in the case of the 421, or 7 light sources of different wavelengths combined into a single output beam. And of course, to put it all together, we have a full line of microscope adapters. Both excitation and emission side adapters are available for pretty much every microscope model out there. If you cannot find the appropriate adapter that you need, please call us. Most likely we have it in stock. If not, many of you already know Sutter is the home of one of the largest precision CNC machining facilities in North California. We constantly design and fabricate custom solutions if needed. One quick note, there is a link there to our YouTube channel. This is a video on how to properly adjust the light guide. Okay, so a brief overview of the products. Let's get into the actual lighting up of our experiment. Here, this is a very cool picture of what's inside the Pentagon when you have LEDs enabled. The 421, so first we're gonna go into the front panel. First thing I like to mention is that the 421 uses the same controller as Lambda Digi 4 series wavelength switchers. So with that said, most of the basic concepts that I'm going to describe will apply to those products as well. On the front panel, we have the intensity control. This actually adjusts the current delivered to the LED module. Please note that for the knob to be effective, the LED control switch must be set in either the on or the TTL position. You have a switch for having internal or external settings for the light source. Internal means that it's controlled via the intensity knob, or externally where you send the command through one of the interface ports. And the other switch on the front panel is the LED control switch. This allows us to enable or disable the LED manually, or to set it in TTL mode, and then the switching would actually be handled by the strobe input on the rear panel. Now, the 421, since each section is individual, you could both set any combination of manual and software configurations. Keep in mind that for the intensity control in the so-called TTL mode or the external mode, the current is a combination of a DAC value setting, which is usually specified in software, plus any manual adjustments made via the intensity control. Keep in mind also that the manual adjustments are in proportion to the DAC value. So for example, if a DAC value, the ranges are from 0 to 4095. If we set a value of 2048, which basically gives us a maximum outlet of 50% attenuation, the intensity knob max would be at that 50% and then lower from there. The rear panel. The rear panel has a number of different BNC connectors and DB connectors on them. So first, let's start off with the interface. The USB interface, which is the factory default, this can be connected to a USB 1.2 computer connector. So anything above 1.2, the 2.0 or 3 would work fine. In most cases, the USB port will be used in a so-called virtual COM port mode. So basically, the USB port looks like an RS-232 port. And the reason that we use this mode is it offers backward compatibility with software that's already developed. The RS-232 port, again, mostly for legacy port, mostly for software that's already been written for the Digi4 controllers. And finally, the TTL or the parallel port. This input provides the full 8 bits needed to execute all the available controller commands. The parallel port provides the shortest latencies between commands, approximately 1 millisecond between commands, but it is not a true parallel port as it's not bidirectional and therefore commands cannot be read back. As mentioned earlier, the default port is the USB, but the controller scans all the ports until it detects a go online command. Now, once this command is detected on that port, then that port becomes the active port and scanning is then terminated. Okay, the other connectors on the rear panel are the strobe input. This is what we put in a trigger to execute the ring buffer, and I'll talk about the ring buffer later on. We have 2 filter monitors that will show us the currently selected filter. On one side, we have the filter value, which is shown in the digital output or binary representation. And a DAC gives us an analog output. So here the voltage representation is from 0 to 6 volts. It's in 16,400 millivolt steps, where each step represents from 0 to 15 filter values. All right, so let's get into actually interfacing it. So first up is the parallel port, the so-called TTL port. And for that, we usually need to have some kind of custom cable to interface to it. This is the rear view of a female connector, DB25 female connector, that is required to plug into the back of the 421. Now, these are the connections that we actually have to make to be able to send all the commands over. So we have here the 8 TTL inputs from pins numbers 2 to 9, and then we need a ground. Here I selected ground pin number 25, but pretty much most of the pins on the lower side of the connector can be used as ground as well. Now, the easiest way to make a cable is to get either an RS-232 cable with a dual DB25 male connectors or a so-called DB25 extension cable. Then you simply cut off one end, making sure to save the one with the male connector, and then connect the wires by either soldering directly to one of these mating connectors, or you could simply use screw-in breakout connector boards like these to make your life easier. Now, the cables, connectors, and the breakout boards are available from a variety of online sources. Another way to connect to the parallel port is using BNC cables, and that would require a DB25 to BNC adapter board. Sutter has such a board available. That's the part number for it. The important fact is that all the dip switches need to be in the up position. Otherwise, the connections would be connected to ground, which would give us an error when interfacing. Like the custom cables, we need, again, all the digital outputs to be connected, and this is a table showing all of these connections. Now, very important note, all of the TTL lines need to be properly connected. Otherwise, the commands will not function. And I say this after spending a lot of debugging time. Commands are associated with decimal equivalents. So this is how we send them out via either the TTL port or the USB. And here's a list of all the different commands that are available. A complete description is available in both the Lambda DG4, DG5 manuals or the 421. Now that we have a physical connection made, how do we send commands? So first we'll start off, I use the Sutter Patch paradigm editor to send out digital words to the 421 to get it ready. First, we create a new paradigm, clicking on the button. Then we insert our commands. First, we insert an amplifier command. In this case, it would be a digital word with the command number 238, which actually means go online. Then we insert a wait period, and this wait period is typically about 500 microseconds, and we want to ensure that the 421 controller has enough time to process each command. And we're going to repeat this for 2 additional commands. One, to execute a filter change immediately, followed by a command to set the default state to all LEDs off. And then when we click on Start Paradigm, it will actually execute this paradigm in order and get things ready. Note that the Go Online command only needs to be executed once unless you power down the 421. Now that we have the 421 ready to accept our TTL commands, let's go in and test it using some routine acquisition. So the easiest way to modify a routine is to actually take one that already exists and duplicate it, and I won't show that here. Then we go into the output channels at waveform window, and we're going to make the following changes. First, we're going to change our digital outputs from individual bits to word. Then we're going to enable the digital outward channel itself. Then we're going to go to Edit Waveform to bring up the waveform editor. This is where we're going to define our timing and execution. And we're going to insert as many segments as we need to specify this command and timing. Please note that the bit word, that's the value, that's the command value that you're going to use. So 0 means LED off, and then 1 to 15 is an actual filter value and attenuation. Now, that was a very simple routine. Now, if we want to do repetitive fast switching, then we could tweak the waveform editor a bit. So we're going to use, in this case, a square wave waveform instead of individual segments. And with a square wave waveform, we could define the value and timing of a pair of pulses. And then this gets automatically repeated X number of times based on the segment duration that we have modified. As you see here, the preview is what actually would be displayed in the routine editor as we're making these changes. Also note that all analog and digital outputs of both the IPA and DPatch systems are fully synchronized. Therefore, the wavelength switching would also be synchronized. Now let's talk about interfacing with the USB port, which is the more common port nowadays. For the USB port, I will introduce a new development which we call the Sutter Lambda XOP. This development includes a dedicated USB XOP, which supports both Windows 10 and Mac OS X. It's an open source procedure file. So here, unlike our Sutter Patch IPFs, this is open for you to modify and change as needed. We have a built-in control panel that allows you to have access to and control the 421, or you have functions that you could directly call from your own Igor Pro procedures. It supports the Digi series and the 421. It's very easy installation. All you have to do is copy the appropriate XOP to the Igor extensions folder, copy the IPF to the Igor procedure folder, and then a Sutter menu will be added to the top of the Igor Pro menu to give you access to this control panel. And best of all, it's free of charge. It's not available on our website yet, so if anybody would like to get a copy, please send me an email. This is a list of all the different functions that can be called directly from an Igor procedure or from the command line, or actually in some of the examples, I will actually call them from Sutter Patch through the Paradigm Editor. Now let's talk a little bit about the Lambda controller panel. This is a GUI-based panel that will allow us to control things via buttons and controls. So first up is a command status indicator. Of course, green means that the command executed correctly, red means that it failed. Then we have device selection and configuration. If there's more than one device connected to the computer, it will show up on that device list. Then you have our filter commands. So here we could specify the individual filters. And if you have the light guide sitting there, you could see them changing from one to the other as you do it. Then we have our ring buffer commands, and this is the heart of this project. This is what makes using the USB as fast as using the TTL. And I'll go into that in a later slide. And then we also have a triggering mode that you could set. And again, I'll explain that a little bit later. And then we have buttons on the side there that allow you to expand and contract the different sections. Okay, the ring buffer. So what is the ring buffer? The ring buffer provides fast latency switching since filter changes are executed by precise triggering instead of sending individual USB commands. Now, as you all know, USB commands all suffer from undefined system latencies that are built into both Windows and Mac OS. The buffer itself is a memory chip. It's a circular buffer. It has a space for a maximum of 100 entries. Each entry is a filter value. When a trigger pulse is detected on the strobe input port, the filter command value will first be executed, and the next entry is primed for execution. Now, as I mentioned, the 421 does have a unique strobe trigger mode. This is unique to the 421. It's not available on the Digi 4 or 5. You could have either to execute on a rising or falling edge. And in addition, we have a special modes that allow not only the level of the trigger signal, but also what happens on the either falling or trailing edge, or basically allows the LED to turn on and then go back on the next edge to go to the off position. Okay, ring buffer programming. For the Lambda 421, that could only be programmed from software. On the Lambda Digi 4 5 series, it could be programmed either from software or from the keypad. A video that illustrates the programming of a 10.3 is available on our Sutter YouTube channel, but the commands are identical for the Lambda Digi series as well. As I mentioned, the 421 needs to be programmed by software, so the first option is to actually use the control panel. So in the control panel, we go in and we click on Start Recording from the ring buffer command section. Then we go and we click on each of the filters that we want in the order that we want them to be executed. And then when we're done, we do stop recording. The second method is to actually write an Igor function that will do that for us. So here I created a simple function. I used an array of ring buffer commands, and then I enter the values for them, and then I send the command to actually load the ring buffer. Now, to execute it, we can execute directly from the control panel here. So first thing we need to do is we need to check and set strobe trigger pulse mode if needed. Then we need to make a connection to the strobe input of the 421 to our triggering source. In this case, I'm using the IPA amplifier. And then we want to click execute. And when you click execute, what it does is it primes the 421 for so-called ring buffer execution mode. Now we could execute a routine or membrane test, which will send out a trigger on the trigger output pulse, and then you should be able to see the wavelength switching with each pulse. Here, in this case, it would be 1, 2, 3, 4, and then it will wrap around to the beginning of the buffer as we keep going. And then finally, click stop to terminate the ring buffer mode. Another way to do it is to use a Sutter patch paradigm. And here we're going to create a paradigm. As I mentioned earlier, I created a function that will actually load the ring buffer with some values, because I'm going to call this function directly from my paradigm. In my paradigm, I'm going to first call that function to load the ring buffer. Then I'm going to execute a command that would actually start the ring buffer mode. It will execute my routine, and then finally a command to end the ring buffer mode. So when we click on start paradigm, it executes this. Here's our scope window with our 10 sweeps. So what I also did here was I connected a BNC to the DAC output of the 421, and I fed it into the aux in of the IPA so I can monitor what filter values were being executed. Now that I'm working with the paradigm, we could tweak the routines for various acquisitions. So now what we're going to do is we're going to first change from the trigger out to a digital out 1 connection. Then we're going to make some changes similar to what I mentioned earlier, except now we're going to be using individual bits, in this case, digital 1, and we're going to use 11 segments to define the actual trigger pulses going to the strobe input. And here's what it looks like when we execute it in 10 sweeps. This is actually in a concatenated view, and you could see there all 10 sweeps shown on the scope window. Now, if we look at the aux in port there, you'll see the individual steps that show what executing our ring buffer, which is filter value 1, 2, 3, 4, and finally going to position 0, LED off. So, in conclusion, the Lambda 421 and the G4 series products offer very fast wavelength switching. The built-in device controller and the combination of Igor Pro, the Sutter Lambda XOP, and Sutter Patch provide the ultimate flexibility for peripheral device interfacing, not just for the 421, but for other Sutter products as well. As I mentioned, my talk was centered around Sutter Patch, but you can use the same interfacing techniques for other instruments and other software systems. Recently, I helped a customer with a Patchmaster system using the parallel port method to interface with their 421. In addition, Sutter has drivers and test utilities available for download on our technical support section of our website. I hope you found this useful, and if you have any questions, please feel free to email me. Thank you.
Thank you very much, Telly. That was very informative. The majority of the audience is still on, even though we are well over time. I'm sorry about that. There are a large number of questions here, and a lot of them are along the lines of, thank you, that was very informative, but then there's questions along the lines of, I joined late, and will this be available on YouTube or something like that? Yes, there will be a recording, and it will be on our YouTube channel and our Youku channel for our customers in China. And everybody who has signed up for the webinar will receive a notification once this becomes available. The majority of questions are for Adair, not quite surprisingly. Let's start with one. Sometimes the glass piece sticks to the filament during the ramp test. What could cause this?
Well, if the filament is getting stuck to the glass, it means that the glass is not properly, the filament is not properly aligned over the air jet and around the glass. In the Pipette cookbook, there is information on making sure your filament is perfectly centered over the air jet. There's information on how to install the filament. We have a video on that on the Sutter Instrument YouTube channel. But one of the things you want to do is you want to make sure that the glass is going perfectly through the middle of your filament. And there are these adjustments on page 16 where you can loosen a locking screw right here, and then you would use the eccentric screw to move the filament block assembly up, as you can see over here, and you can also move the filament block assembly front to back. And that can make sure that the filament, you can make sure the filament is perfectly centered around the glass and not touching it. If you have a small filament, maybe it's too small and the glass is too large. If you have a 2 millimeter box, but you've got 1.5 glass, you don't have much wiggle room. So one of the other things to look for here, there's a chapter called Crazy Lab Lore, page 75. Let's go to that. And that will also show you how to reshape the filament and make sure the filament is properly shaped and isn't squashed. What can happen is the filament can get squashed like this right here in the center, and you can pull the wings out and stretch it back out so then it is a box again, and you can use these flat needle nose pliers that I really like to use to reflatten the walls if that needs to happen. So you can send me a picture of the way the filament's installed from the top and also from the side, like looking through the pipeline at the horizontal approach at the horizon, and then I can tell you what most likely needs to be adjusted if you can't figure it out.
Okay, thank you. Another question, with resistance changes when I pull 3 or 4 times in a row. If I wait until the temperature drops, then the resistance is more stable. How can I do a stable program to avoid that problem? And then the same customer asked another question with the same program. Some days we have pipettes with the desired resistance, but other days the resistance increases or decreases. Is there any reason for that? We're aiming for long taper pipettes to use in vivo recordings. I suspect that the answers are related.
Yeah, with the P97 or the P1000 pullers, if this is those filament-based pullers, I assume,
Yes,
the jaws will heat. Okay, the jaws will heat up, and so when you first use the puller in the morning, the jaws are cold, and if your program's somewhat unstable, as you pull more and more pipettes, the jaws get hotter, and if the program's a little unstable, it's more vulnerable to those heat shifts in the jaws, and that can cause the pipette resistance or taper lengths to change. The P1000 has a preheat mode that you can use, so you can heat up the jaws up to 70 degrees centigrade. It holds it at that temperature, and then hopefully that'll stabilize it. The other option is to increase the purging of the humidity control chamber before and after the pull. Instead of the default of 5 seconds, you can jack that up to about 10 seconds or 20 seconds, and that helps cool things off and maybe keep the temperatures a little more in the midpoint around like 45 degrees Celsius when you're pulling your pipettes. You can present the parameter settings to me, and I can see whether or not it has to do with the parameter settings. It could also have to do with the way the filament is installed in the puller, but most likely there's an issue with the parameter settings. Now, if the puller's old, sometimes the pulleys can freeze up or the oils have built up and they've polymerized and you've got some friction going on somewhere, but most likely it's a programming issue. Again, they can get a hold of me with the actual parameter settings and I'll help them out.
Thank you very much. There's a few questions for Telly. One question, why Igor Pro?
Okay, so many of you know our Sutter Patch development is all around Igor Pro, which offers us tons and tons of flexibility, in particular with being able to get data out in some nice publication quality. So when I was approached about this 421 project, it was to initially add it in the Sutter Patch development. Well, we slightly changed gears on that and we made it an open source development. So it allows us to share the project or the development with other people who use Igor Pro, and we could take full advantage of it in Sutter Patch. I think this is going to be a model that we're going to be using moving forward for a lot of the other Sutter peripheral devices that we want to support in Sutter Patch.
Okay, then here's a question for me actually about the dendrite. Is it sold individually and for how much? Yes, it is sold individually, and the US price, remind me, Telly, was it?
I believe it's somewhere around 6,900.
If you're international, then your local distributor may have different pricing. The next part of the question, does this include software analysis package? Yes, it includes SertaPatch, comes as a complete package. What is the native acquisition mode? For example, ABF or CSV. It is the SertaPatch data file format. You can export your data in ABF and CSV. And does the software come with event detection? That is spike counting. Yes, it does come with offline event detection. And we have just implemented event detected acquisition mode. Is it compatible with Windows 10? Yes, absolutely. And Mac OS. And what's the interface for Dynamic Clamp? The answer is, unfortunately, the Dendrite does not support Dynamic Clamp because Dynamic Clamp requires a lot of computing power. For Dynamic Clamp, you would need to get a dpatch system. Those were all questions from the same customer. I will get in touch with you by email and we can discuss that further. Let's get another question for Adair. There's questions still coming in, and I'm pretty sure we're not going to get to all of them during the Q&A session here. When should the rubber pad be replaced?
The clamps on the puller bars, the rubber on the back, they can just check it and see if it's cracked or if there's a deep depression in the rubber. And then sometimes the rubber gets really old and hard, and so it's not really grabbing onto the glass. But it's a good thing to just take the knob off the washer and then inspect the rubber padding and see its condition. You don't just replace the rubber padding. We actually just send out the clamps. It's a bit easier, and we can make sure that just the right kind of padding is attached properly, and it's got that beveled cut on it so the glass doesn't grab it when you're loading the glass under the clamp. I think the U.S. price is about $50 for a pair of clamps, and the knobs, I think, are about $35 each.
Okay. And I would like to add, sometimes I've seen pullers in the field where the metal shows through that little groove in the rubber. That's when the
Yes.
should have been replaced long ago, because once the metal hits the glass, the risk that you crush is very high.
You can
Okay,
always
another
tell
one.
when that's going on because there's a lot of broken glass underneath the clamps.
Okay, thank you very much. Another question for Telly. We talked about operating system compatibility for SertaPatch. You mentioned Mac OS X. How about Catalina?
Yes, we have everything in place for Catalina, so we've gone through all of the proper signing procedures required, and that was actually a pain in the neck, but it's all done for both SertaPatch and for the Lambda XOP. So Catalina is no problem.
Okay. And then another question for Adair. Brilliant presentation, very useful. We like to hear that. Does it make sense to keep your instrument on for some time before starting to pull a pipette?
With the filament-based pullers, no. There's a filament transformer inside the chassis which does not warm up. The only thing that gets warm over time and warms up are the brass jaws. And sometimes you will see, if your program's a little unstable, the tips getting smaller and smaller with consecutive pulls and as those jaws get hot. The laser puller, yes, you have to turn that on, and it's good to have it warm up for about 15 to 20 minutes. I have myself turned it on and been in a hurry and thought, oh, I can just pull the pipettes, no problem. And it makes a huge difference. So it's really important to turn the laser puller on and have it heat up for 15, 20 minutes. So make sure you give yourself that time and you're not in a crunch, and you give the puller some warm-up time. If you don't, what's going to happen is you're going to turn it on. The program's not going to be pulling the pipette with a proper taper length, and you're going to start adjusting the parameter settings, and then you're going to get lost, and then you're going to end up back to where you started, hopefully, where the program was actually good. All you had to do was let the puller heat up. The laser has to heat up.
Thank you. And another one for you. Can I send my puller P87 for maintenance? It is old.
Yes, we do on the newer Rev pullers that are still in production. We do repairs and we do refurbishing of the pullers. Depending on the extent of the repair, it's usually 500 to 1,500. Refurbishes tend to be between 2,500 and 4,500, depending on the age. A P87, we will do a repair. We can warranty and guarantee the mechanical repairs, but the electronics we can't guarantee. Plus, those pullers, there are many electronic parts we no longer have. We don't have them available. They're not made. Depending on what needs to be repaired on the Polar, I can give them advice into whether it's worth them putting money into something that old.
That's always a problem with making electronics. Obsolescence is an issue. We oftentimes buy large quantities before parts go out of production, but for the P87, there's a number of components that went out of production so long ago that we are out now. One more for you, Adair. I pull sharp electrodes with the P97 and a resistance of about 40 megohms. My electrodes keep drifting to lower resistances.
Okay. I'd have to see the parameter settings, but what might be happening is as you pull more and more pipettes, the jaws get hotter, and they might have a heat setting that's high enough and a cooling setting or delay and pressure or time and pressure setting, which is cooling the glass, that is too low. And so what you end up with is this bad marriage between too high of a heat and too low of cooling. And then what happens is you end up pulling tips that are a little bit more, they end up being blunt because the cooling is actually allowing the glass to pull down to a fine point. And once you overwhelm it with heat or underwhelm it with cooling, you pull out like these little stubby tips. So that might be happening. The other issue could be that they're just pulling way too hard on the glass, overwhelming the cohesive factors of the glass and kind of breaking it off.
Okay, one more question for Telly. Do the same steps that you showed for the 421 apply to the 821?
Yes and no. The 821 does not have a USB port. It does have TTL inputs via BNC connectors on the rear panel that you could send commands in and set in the ring buffer, but it's slightly different ways to talk to it. Honestly, I don't have much experience with interfacing to the 821 as I do with the 421, but I would think that many things can be replicated.
Okie dokie. Let's do two more questions and then address the rest by email. And there's so many more questions for Adair, so let's do two for Adair. One is, hi Adair, it's a great and funny presentation regarding the replacement of filaments in the P87. What do I need to do following, I interpret the question as, what do I need to do after replacing a filament? Just follow the instructions of the cookbook with a ramp test?
Yes, follow the instructions on how to install it, making sure it's centered over the air jet, and you need to pull a long pair of long tapered pipettes to see if the filament is truly evenly heating and cooling the glass on the right and left evenly. So it's pages 17 and 18 in the Pipette Cookbook, which provide those details. Of course, you do need to run a ramp test too. So yes, make sure it's centered, run your ramp test, find out the appropriate heat for that filament, use pages 17 and 18 to make sure the filament is centered, and then proceed with writing your program.
Okay. Another one to you. Is it possible to bend borosilicate pipettes? Is there a way to bend them maybe with a P1000?
Yes, I haven't tried bending with the laser puller, but I assume you can. I just have done that with the quartz glass, but with the P1000 and the P97, on the webinar we have called Achieving the Impossible, those details are given on that webinar. Maybe I think 3/4 into the webinar, I show people how they can bend the glass along the shaft where it's not melted and pulled, and also along the taper at different locations.
Questions still keep coming in, so let's do one last question and then keep it open for people to finish typing. Do or should we sell a standardized maintenance kit for each model of puller, which could include the lithium grease you showed, replacement gas clamps, washers, a filament, etc.? And might also
that might be a good
USB stick containing videos or the links to the YouTube channel with your instructional videos.
Yeah, that's a good idea. One of the main ingredients is ethanol, and normally we don't want to ship that. 70% ethanol.
Yeah, it wouldn't make sense to include something in a kit that is probably available in any lab.
Yeah, but extra spare parts that, maybe I could put some sort of kit together that would be beneficial to a lot of people. I can definitely consider that and figure out what we would put together, and maybe there'd be some sort of kit that might be some spare parts. Yeah, it's a good idea.
Great suggestion. We'll discuss that. And with that, what I would suggest is let's leave the webinar open for another couple minutes so people can finish typing questions. As I said, they still come pouring in, so we need to address them by email. And then we'll close the webinar about 3-4 minutes from now. Thank you very much, everybody, for attending, and goodbye.